好像也稍微了解一些，可是它当然还不是完全了解，多了一些 free paper。
All protogalaxy.
Okay. Oops. Okay, so hi everyone. I'm not going to explain Protogalaxy in detail. I've just written it here because I think Zach did a good job explaining Protogalaxy, and I think Jern will follow up with the rest of the details. So what I am going to do is explain like how Protogalaxy or Protostar type folding works, and try to give like an intuition on how these schemes are created. And just like a big disclaimer, most of this material is stolen from a talk given by Liam. I'll just write his name here, and Liam is the co-author of Protogalaxy.
Okay, it's online video.
Yeah. So quick recap, like Chi mentioned about nova, supernova, hypernova. How is Protostar or Protogalaxy different from all of them? So in Protostar type of folding, you have like you fold arbitrary polynomial maps F or fold arbitrary polynomial maps F.
Fold what? The first bit.
Arbitrary. So any arbitrary.
Arbitrary.
Okay, arbitrary polynomial maps F. So what that means is that F can be like a d-degree polynomial, and it doesn't require structure. So it doesn't have to be like an R1 CS or CCS. So you're not restricted to like R1 CS, like not restricted to structured. So Protostar is kind of a generalization of nova type of folding to more like arbitrary polynomials kind of systems. And Protogalaxy is just multiple Protostar. Wait, let me write. Okay, Protogalaxy is an extension of Protostar to fold multiple Protostar instances. So anyway, recap or math. So I'll quickly go over like the basic math. You have like some polynomial map which goes from Fm to Fn. Let's say the degree is d. This is a polynomial map. Then you have like some Cm is a homomorphic commitment scheme, like additively homomorphic commitment scheme. And then like you have two things. One is you have omega, which is the witness, and then you have phi, which is Cm of omega, which is a commitment to the witness. To omega, and together phi comma omega form the instance. So phi is something which is known by both prover and verifier, and omega, the witness, is only known by prover. So you have this, and now this is instance. You can say the instance belongs to this set R, and the equation that's supposed to hold is that f of omega should be equal to 0 for any valid instance. So this is like the basic premise of Protostar, and like you can use this f to write like R1 CS constraints as well. So like if this was R1 CS, then example, CS. You can write Fi of omega equal to it's like Hadamard product. So it's a general system which you can also use to express like R1CS or other type of constraint systems. And yeah, the reason why this type of folding works is because you have this CM, right? This homomorphic commitment scheme. So if the prover wants to prove that the commitment of A omega plus B omega is equal to something, then because the scheme is homomorphic or additively homomorphic, what it can do is it can compute this as this, let's say omega 1, omega 2, omega 0. So basically what's happening here is that because if the prover wants to prove like the commitment of this of a linear combination of the witnesses, it doesn't depend on the dimension of the witness. They can only use the commitment to like the witnesses that are being used to linearly combine to prove the commitment of the addition of these witnesses. Let me explain that properly. But anyways, like this whole thing is independent of the length of omega, so it can be done in like efficiently.
In what?
Efficiently. Okay. I'm going to rub all of this, or I need more space. To explain like basic folding. Okay, so let's say we have two instances, phi 0 omega 1 and phi 2 or phi 1, phi 0 omega 0, phi 1 omega 1. And we want to fold both of these instances together. So one basic way is that we take a line segment which goes through both of these instances. So equation for a line which would go through both of these instances can be written as like omega x to x, oh wait, 1 minus x. Omega 1. So this like omega of 0 here would be equal to omega naught of 1 equal to omega 1. So you take both of these witnesses and take a line which goes through both of these witnesses. So this is how, like, you're trying to combine both of these instances together, right? So one way you can do is just take a line and say that a random evaluation of a point on the line would be like the folded instance.
Sorry, it says in protogalaxy or galaxy?
This is both of them. Like, this is the general way how folding works in like these systems. So let's say you have like this folded instance, whatever. Now the commitment to this folded instance would be like you do like Cm omega x here. Now because the commitment scheme is homomorphic, like you can divide it over here. So it would be makes sense, right? Because of like the linearity of the commitment scheme. Now the other thing that should happen, like if you want to make sure that this is a valid instance, right? The combination or the folded combination of both of these. So for this to be a valid instance, you have to like calculate this polynomial map over the instance. And if you try to calculate this, like let's evaluate it at omega 0. So omega 0 is omega naught. So this should be equal to f of omega naught, which you know equal to 0. F of omega 1 which be equal to f of omega 1. And this is 0 because omega naught and omega 1 are valid instances. If you take it for like an arbitrary omega x, then you can describe it as 1 minus x So if you calculate f on this folded witness, then you can write it in this form. So if you evaluate this at omega 0, you just substitute x equal to 0. So this is 0, this is 0, this is f of omega naught, which would be equal to 0. If you evaluate it at x equal to 1, this is 0, this is 0, this becomes f of omega 1, which again has to be 0. So this can be simplified as so what you're saying is that if I can find the qx such that f of omega x can be expressed as this, then the initial witnesses that you were folding, like this omega naught or omega 1, those would be valid. Like if you can find the qx such that this equation holds, then the initial witnesses are valid, like the initial instances are valid. So you don't have to check both of them individually, you can just check for the folded one. Make sense? Okay. Now how do we do that? This is kind of this shows up in a lot of other proving schemes, right? You have to show that there exists a quotient polynomial such that this equation is valid. So yeah, the prover would calculate qx, the prover would commit to or whatever, send qx, the verifier will return with the random challenge gamma. So anyways, so so you're saying that fx, if expressed as this, it will satisfy these two equations, right? It will satisfy these two equations. So this is one form of writing like f of omega x, and if it can be written in this way, then you're pretty sure that you can be sure that the initial witnesses were valid because the initial equations will be valid for omega 1 and omega 2. So if you can find this qx, then you don't have to check both of these equations, you can just check this equation.
Why do we need the last term, like last x? Yeah, because that two term is in absence, so I have two equations.
There are more. 2, 3, 4, 5, 6.
Why do we need this? Because like if omega evaluated at some other point, it might not be 0, right? You need to make sure that like this represents this encapsulates values for all x, not just 0 and 1.
Okay, that's fine.
Yeah.
0 and 1 has to be
But for 0 and 1, it has to be 0. So this has to be of this form. Okay. So yeah, so verifier. So to get this folded instance, right, the verifier will sample a gamma. Your folded instance would become omega of gamma, say omega, which again you substitute to that like the equation of the line. Folded commitment would become phi of gamma, which again you substitute in the equation of the line. But now the problem is that if you calculate f of gamma dash, this would be equal to like this value, right? So gamma 1 minus gamma q of gamma, which is not equal to 0. So if you remember, like in the definition of an instance, we're saying that f evaluated at the witness should be equal to 0. But if we take this folded instance, then if we calculate f of like this folded witness, it doesn't evaluate to 0, it evaluates to like this value. So this whatever omega dash or phi dash comma omega dash doesn't belong to R. Like it's not a valid instance, so we cannot use this. So that's why we introduced this error term like in R1CS or whatever. Like this is exactly what Dr. Gu explained for R1CS, but for Protostar, just to develop like some intuition of Protostar. So anyways, you define a new term E, which is the error, and you relax this equation by saying that f of omega, instead of being equal to 0, let me actually rewrite this. So you redefine your instances as these relaxed instances such that like now the instance contains the values phi, which is the commitment, an error term, and the witness, and you say that instead of the function evaluated at the witness, instead of it being 0, it will now be equal to e. Okay, so okay, now what changes? Like how do we fold this relaxed instance now? So this equation remains the same. This is how you will fold like the witness. This remains the same. This remains the same. For this, now this would be equal to E naught. This will be equal to E1. This will be equal to
So what you're doing now is that you're folding only the witnesses.
no, we're folding the witness, we're folding the commitment, and we're folding E. So we started by just introducing this term, right? Like saying that if we just extrapolate the witnesses on a line and take a random evaluation of that on the line, can we use this as a folded instance? The answer was no, because if you evaluate f on this like any point on the line, this will not evaluate to 0, which means that it's not a valid witness. So we say that we change the definition of a instance now. So instead of it being 0 at all points, we say that it should be equal to this term called E, and we introduce E into the equation. So whatever error we get, we define like this new E for to make sure that the function evaluates to E instead of 0.
So what you're trying to do now is you're trying to show that a way to fold instances only.
Such that such that some relation remains valid.
Okay, thank you.
So you're basically trying to the institution and so why we need to relax the relation?
Yeah.
Why relax the answers?
Yeah, exactly.
Okay, got it. Thank you.
So yeah, if we just linearly combine like the witness and the commitment, then we won't get a relation which still satisfies this. So that's why we need the error term to create this relaxed instance which satisfies all the equations.
Because of that last term, right?
Yeah, because if we just linearly interpolate, we'll get this last term which is not equal to 0. Yeah. So this is how this is exactly what Dr. Guo explained, but for R1CS, but this is more generalized for like protostar type of polynomial maps. So this is why we need the error term. But now let's try to generalize this for multiple instances, like what changes in case of multiple instances. So I'll just quickly explain this. So in this equation, like any one of these equations, you can think of 1 minus x into x as the 0 polynomial of the values in which you have like omega naught and omega 1. So this would be a 0 polynomial for like the instance values at 0 and 1, right? So zx, which is equal to x into 1 minus x, can be thought of as like a 0 polynomial for a set which contains 0 and 1, and 0 and 1 are the points in which the witness is being evaluated. So this is for the two instance case. You can generalize this into saying that let's say we have k witnesses or k instances that we want to combine. We define zx as x raised power k minus 1, and we take, instead of taking like 1 minus x and x, we take the Lagrange polynomials Lix, which will be equal to,
this is the protogalaxy part, right?
yeah, this is the protogalaxy part. So a protogalaxy is like combining multiple instances of protostar. So I'm just trying to create an intuition like why does Lagrange polynomial shows up, right? Because someone asked me last time. So in the two kind of instance case, you can think of x and 1 minus x as the Lagrange polynomials of like this equation. If you want to generalize it to k cases, you will write the equation as x raised power k minus 1. And all the.
So next we will you mode zx, right? So to remove, so you eliminate this.
Yeah, this is the part which contains like mod zx, right? This is like zx into qx.
In this case, zs is not exactly a 0 polynomial, but you're actually using that to represent the equation. Okay, got it. Thank you.
think of like Zx being a zero polynomial of a set, and all the solutions to this x is where the witnesses will be evaluated. So in the beginning we took like Zx as this, and the witness or this line is the evaluation of the lines at the points of this or at the zeros of the zero polynomial is the witness values that we are trying to combine. Now we take the zero polynomial and as this, and the evaluations of or the roots of this polynomials will be the points at which we'll combine like the witness polynomials,
Okay, so
witness values.
got another one. Didn't we then
Okay.
create a relaxed form introducing that 0 and 1 is no longer 0 but an error term? Do we, in this case, do we temporarily forget about error term or is
No, we didn't. Okay. We introduced the error term, but we're still evaluating it at 0 and 1, right? The way we're combining is that we're multiplying the omega naught term by 1 minus x, which is like one of the roots of this zero polynomial, and the other term we're multiplying by the other root of the zero polynomial. But the error term comes when you're evaluating it at a random point in this like interpolation. So the point that I'm trying to make is that here we use like x and 1 minus x to combine these both witnesses, right? But x and 1 minus x can only be used when you have 2 points. If you want to generalize it to k points, then what you can use is that you can take this as the zero polynomial and take like the Lagrange polynomial for each of these roots as the coefficient that you're going to use for combining the witnesses. And the reason why they maintain the same property is that like what's happening here, like at one point, like at x equal to 0, this term is 0. At x equal to 1, this term is 0. If you take the Lagrange polynomial and let's say I define my new witness as
okay, I see it now.
so if I define my witness as this and I calculate the values of the witness at the zeros of this polynomial, then each value will correspond to like one of the witnesses that I'm trying to combine. Make sense? So this is kind of an analog of this, but for a generalized k case, combining k instances. And you can rewrite your equation as, so omega x is this. Wait. So f of the sum of this Lagrange basis polynomial, which is your new folded witness, will be equal to, like this is this part, the sum of all the values with the Lagrange basis plus this qx zx polynomial, because for each of the points you want this to vanish, right? So that's why you have the zx over there. And now like it's the same thing, you will try to prove an existence of a qx, and then you'll do the same thing, like the verifier will sample a random gamma, and then you'll check the gamma, and then you'll have your new instance as omega dash, which is this, or omega gamma. And this is how you'll calculate like omega dash, taking the combination in Lagrange basis, just to make sure that when you evaluate it for this equations and you evaluate it like each of the points of the zero polynomial, only like one of the terms is non-zero, all the other terms will be 0.
So hang on, can you remind me like why you're writing those two Protostar again?
This?
Yeah.
This is the relaxed instance.
Oh, okay.
So we started with an instance which was just the commitment and the witness. We said that this can't work because if we evaluate the f function for a linearly like kind of interpolated folded instance, we won't get 0. So we need to introduce this error term just to make it more generalizable. So we introduce this error term. We say that the error term is now part of the instance, which also needs to be folded. So if we start with an error term e, once we do this, we'll get another error term e dash, which will be like the folded error. And yeah, I explained how you do it for 2 terms. Like if you only have 2 terms, this makes sense, right? Like you just prove the existence of qx, and that is how you can kind of fold all of this. Now it can be generalized to any k, by taking instead of x1 minus x, you take like the Lagrange basis of a polynomial which can be defined as x raised to k minus 1. So this is just to show that all that can be generalized to k terms by taking it in Lagrange basis.
Sorry, one more question. Like the last step, omega, omega, W to E, omega,
Gamma.
gamma. So that is evaluating at a random point. Is that?
Yeah. So gamma is something which will be sampled by the verifier,
Okay.
and he'll send gamma, and this is like you'll evaluate omega at this gamma,
Okay.
and now this omega dash is your new folded instance.
Okay.
So instead of checking all these k instances, you'll now only check the folded instance.
Okay. And because of it being additive homomorphic, you can also say that the folded the commitment of the
Folded commitment will also be like, it will be an expression like this.
Okay.
So instead of 1 minus x and x, it would be like the Lagrange basis.
And the E prime.
E you will evaluate by like evaluating this. So you evaluate this at gamma.
Okay.
This will give you,
New E prime.
yeah, this will give you this value at. So for a two-thing case, like your E prime would be, is it there? Like gamma 1 minus gamma into q of gamma. That would be your new error.
Sorry, I have so many questions. I'm sorry. One more. Because E somehow requires you to have folded witness prime. And witness prime is private. Do you also have a committed E prime?
I don't think we have a committed E prime, no.
Okay.
You only have an E prime. That is the next kind of optimization. So the problem here is that you have to store this E prime now, right? And E prime is like a n degree vector, or not n degree, but length n vector. So another thing that you can do is fold E on itself. Yeah, from using beta. Like if you remember Jern's talk from last time, he mentioned these betas, right, which can be used to fold. Like I can explain that as well. But that is where things get more complicated. Okay.
Wait, so you remove the beta out to this?
The beta is not here yet. So this is just to give you an intuition of how like normal, simple two instance folding works and how it can be extended to k instance folding, like the general intuition behind all of this. Now,
a step-by-step intuitive.
yeah. Now the problem is that this is a n length vector,
Okay, so that's where beta comes in.
which is very large. So if there's a possibility of reducing the size of n, then that would be good. So that's where beta comes in. So
the size of the n like vector depends on the circuit size, or like how.
yeah, so like for example in R1CS you will have the number of rows, right?
Oh, okay, that makes sense. Yeah, sorry, thank you.
So n, right? There's a small case, n, right?
Yeah, sorry, this is n in my handwriting. So yeah, to make it more efficient, what you can do is you can fold E in itself or something, I don't know. So what this means is that instead of E being like the sum, like f omega, E can be defined as a random linear combination of like each of the rows in F. Now I'm not going to go into a lot of detail, and again, like this is a random linear combination, right? So if this is wait, what? Okay, so for the normal instance, if you take a random linear combination and you say that this is, let's ignore E, and this is equal to 0, then that means that RLC. That implies that each of fi omega would be equal to 0, right? Now you want to generalize this for the relaxed instance. So for the relaxed instance, you'll have something like sigma fi omega. Somehow you'll use this to calculate your E, and you somehow want to fold this on itself, and yeah, I don't think I can explain this properly, but I'll give you like some background on how this happened and how this like how is it different in Protostar and Protogalaxy. Like in Protostar, what they do is,
Yeah, this is the most important part.
Oh, doing well.
so you have to somehow calculate this value, right? This random linear combination of each of the rows of your polynomial map with this beta, like some random power of beta. What Protostar does is that it defines capital beta, which will be a part of the instance later. But they define this capital beta, and like beta should have length which is small. Like it shouldn't be a very large vector, because that's what you're trying to do, right? You're trying to reduce the size of E. And yeah, and like there should be some polynomial which maps values from this beta vector to get like values of like the powers of beta that you're going to use in this random linear combination, because you can't give the whole beta, right? You're trying to somehow create like a smaller version of this beta that you can use to fold this in itself.
Okay. So beta is a small length of vector, and g of I of beta, you just take one element of beta. Wait, hang on,
I'm going to define beta.
Okay.
So beta in Protostar is defined as two sets. So first set, this is something that John explained last time, but it contains like powers of beta up to beta raised to 10. So instead of taking like all the powers of beta, which would be like n, you take two sets, which is like first set would be powers of beta up to this root n minus 1, and the other would be powers of beta from root n up to, I think, root n into root n minus 1. And what you're trying to do is, just using these two sets, you want to recreate all the powers of beta. So in this case, like if you take any two values from these two sets, you can create like any power of beta up to n. So in Protostar, this gx or g beta polynomial would be something of degree 2 and length 2 root n, like beta length 2 root n. And both of these can be used to recreate like any powers of beta, beta I.
Oh, okay.
In protogalaxy, your like beta vector is so beta is for like all powers of 2, which would be like a log n length vector. And then if you want to create like recreate all powers of like any beta I, then you do like the binary decomposition of I and take like corresponding values from here. So your g beta polynomial, which is used to create like all values of beta, would be degree of log n.
Really care about the degree of GI beta, because in protogalaxy beta is just in the running in an instance. So
Yeah, so this big beta is the one which is running in the instance, and like so let's say you have two instances, right, which with different like this big betas that you want to combine. And so what we were doing here is this kind of value, right, like this kind of constraint. Over here, I'm guessing like we're doing something like this, and yeah, we're combining two of these instances into like whatever our new instance would be. So like you can think of it as a polynomial in like the degree of beta or something. So I forgot what is the point that I'm trying to make.
So, okay, so I'm trying to guess, I'm guessing that beta is used to linearly combine the vector of errors to form one single number, one single field element.
Yeah.
And
Yeah, the point of beta is to combine all of these instances into one field element. Yeah.
okay, so both Protostar and Protogalaxy uses different approach and
Uses different.
but- oh, it's okay, we'll find out.
Yeah.
No, that is a good question. Why do they use different approaches? I think like Protogalaxy uses.
Why are they using different approaches? Right?
Okay. I think all right. So why Protostar don't use this one, right? Because the degree is too high.
Okay.
Yeah, degree too high. Here is degree just 2.
Okay.
So saying that the additional folding cost is lower.
So
Alright.
oh, so that means that in higher degree Protostar doesn't work properly because and that's why.
Yes. Protostar deliberately use this part, and they know that kind of a tensor structure, but they just use this one just to minimize the degree of.
Yeah.
But in Protogalaxy, using another approach to introducing beta. So beta actually outside of the protocol, but here in Protostar, beta is an additional step of the protocol going to be folded. So by Protostar, so before folding, you have to add 2 more additional steps to the protocol to deal with this beta stuff. But in Protogalaxy, they just lifted the beta out of the protocol. Right?
So the protogalaxy are okay with more degree.
Yeah. Yes.
Outside cooling system.
Why are they okay with that?
Because
Yeah,
they
I
are
think
outside
I think.
protocol.
Yeah, I think they.
Ayush will-
No, I will not explain. But I think like the point was that Protostar was trying to like they thought that this is the decomposition of beta in which you can kind of recreate this whole polynomial in order n steps or something. But you can somehow do it using this as well, like this decomposition.
Okay, and
But I'm not sure how.
why does the protogalaxy one is locked in again the degree?
Because if you want to recreate any arbitrary like power of beta, like beta raised per I, you need like it's possible that you need log n elements at the maximum.
Yeah, in Protogalaxy, beta will left part. The beta will put into here.
Yeah.
But in Protostar, beta is inside the protocol. It's different.
So I mean,
Okay.
the proof size is bigger because the Protogalaxy because they include the beta in the minutes at the instance.
What size?
The proof size is going to be the instance size or whatever.
Yeah, instance size kind of a little bit larger, but
Which
it's not.
contributes the proof size.
I think. I don't know.
Okay, so okay.
A good question.
No, just trying to make sense of this.
I think in both of them beta is part of the instance. Like I'm not sure, I didn't read Protostar, but in like Protogalaxy beta is part of the instance. But yeah, the point is to reduce the size of E, and if you can decompose beta like this, then you can reduce the size of E. Like instead of it being n, it can be log n, and then your E would be just single value
So in protogalaxy, beta is not in the what proof again? In the
So
instance.
here is
beta in Protostar is not okay. In Protostar, beta is in the protocol, right?
yeah.
But in Protogalaxy, beta is in the instance. So lift the beta out of lift out the beta, put it into the instance. I think it's smarter way.
Interesting. When you mean
Proof
intense,
time
you mean
will be
it's the errors or
I don't know how to say it.
So having another one.
I think it's a
what do you mean by instance? You just want to make sure.
Instance is this.
Oh, okay.
Instance going to
Like
be-
this tuple,
Yeah.
and an instance is valid if this equation holds.
Okay, but the protostar is in the verifier.
Yeah, but beta is in the protocol.
Yeah, in the
Yes, you're right.
Alright, the power shot.
Protostar.
Wait, actually, I've got another question. Please go on. I forgot the question.
Oh, this is the end. There is.
I have a. I forgot. Oh, this is awfully similar to Peterson computational.
No, there's no elliptic curve here. It's just like this is a random linear combination, right? It's, this is there in a lot of.
It's not a elliptic curve field. Okay.
Yeah.
Good.
But the point of doing all of this is to somehow reduce the size of E. Like one way, like if you do it just like this initially, like you'll have to give the full error term, right? Which will be like the number of rows, whatever. It will be large. Now you're trying to fold the error term somewhere by taking the random linear combination of all the rows. And you have to introduce this beta randomness in this. And now what you're trying to do is somehow like, fold this beta itself to use the minimum number of like beta terms in your proof.
The benefit from that is that we don't have to commit to E.
Yeah.
Yeah.
That is one less commitment.
Okay.
And I think like one less commitment when this is linear. Like when the like f function has more degree, I think it might even have like more terms.
Sorry.
If I remember correctly. No?
I don't have one more. Is it the entirety of the protocol or you're missing?
This is not the protocol at all. Oh. This is just like the intuition behind like how does beta come into the picture, or why do you like how do you combine k terms, like why do you need a Lagrange polynomial or whatever. Okay. The protocol is what Zach explained last time.
I thought it made it so easy that finally I got it, like, you know.
No.
So where does beta in it again? Like you use instead of that.
So your error term is this row of error terms, right?
Yeah.
Like this f of omega for each row. But you don't want to send like the whole, or you don't want to keep the whole error term as an instance because it is an n length vector. So what? No, so instead of that, you take like a random linear combinations of like the all the rows and use that somehow as the error term or whatever.
So it's still the same. Like in Protostar, you send like root n and combine it to beta to the I.
Yeah.
To the n, and now we have instead of n thing, we try to combine. It's like binary representation.
Yeah, in Protostar you have 2 and like your this G polynomial will only be of degree 2 because you only need 2 terms to combine. Over here you'll need log n terms to combine. But somehow they do something here efficiently. That's why they don't use like the root n decomposition. Like I'm not exactly sure why he didn't explain in the talk, but yeah. I mean this is what Zach was explaining last time. Like if you remember the POW function that Zach was explaining, right? This is where that comes into the picture.
The version is much clearer than that.
Yeah, because I didn't explain the details.
So omega x actually is the multiplicative subgroup, and
No.
when is
Omega is the witness. There is no subgroup.
I see.
The only subgroup is one formed by X for the Lagrange base.
Okay, so omega x equals to that Lagrange form is to make sure this interpolation is correct, and you can verify with that random gamma.
Yeah, this interpolation is correct, and you can express it in a form in which, like, if you calculate f of omega x, then it comes in this form.
Yeah, to make sure all the e's to evaluate to do by the interpolation correct.
Yeah, like if you evaluate it all at all the roots of this polynomial, then that should be correct. And if you like take the general kind of evaluation at any like random x or arbitrary x, then you can express it in this form. And if you express it in this form, then you only have to like prove the existence of qx or whatever, just to prove all each of these instances. And yeah, you take a random evaluation of this as the folded instance. But this is like a very high level overview of like how you do protostar or protogalaxy type of folding. Why do you need Lagrange polynomials when you're doing protogalaxy? And like where do these betas come from? Like beta is the next step after you've introduced the error term. Like that was the point. That's it. I'll just rub it off.